Here is more of the study guide plus a couple of questions that are problem solving that I have pretty much set up for you. This first free body force diagram is very, very simple, although you have two books sitting here. So right now we're going to talk about the force that this book on top is exerting on the book on the bottom, right? Because it's not pushing through the book, so it has a normal force here, and it's already exerting. It's already showing you what the force is of this book, so we don't have to multiply by 9.8. It says book one has a weight that's pushing down on the book of 40 newtons, and we could say it's pushing downward. Let's call up positive, and we'll call down negative. Okay, so book one is exerting a downward force on book two, and here it is. So the magnitude is 40 newtons, right? It's only pushing down with 40 newtons, and like we said, it's pushing downward or negative, right? Book two is holding book one in place, so it's exerting that normal force. It's pushing back up on book one to keep it at equilibrium. So it's also exerting 40 newtons of force back on that book one, and it's pushing upward or in the positive direction, okay? Now we're going to look at book two on the desktop. Now book two has two masses here. So it's book one and book two. So that extra force of 40 newtons gets added to the 50 newtons, right? Both books are pushing down, and book two is accepting that and pushing downward. So it's exerting a force actually of 90 newtons downward on that table. And then the table or desktop pushes right back up on that second book with 90 newtons, and it goes upward, and it's positive. Okay, so that's a pretty simple idea. I think you guys can handle that. If you have any trouble, please let me know. We'll move on to the next piece. Sorry about the little squiggle there. I didn't realize I had that there. Let's get rid of it. All right. This is just a simple, I don't think I can do both sets of questions at once. These are true-false questions with italicized words. I'll underline the italicized words. There's that, and motion of the object, less affected. Oh, sorry, can't do that yet. It'll go away. So let me do these first couple first. A fluid exerts a drag force on an object, moving through it in the same direction as the motion of the object. So an object's moving down. I don't really like that color. Sorry about that. How dare I use that color? Let's use a bright color. This object is moving downward through this fluid, right? Through this fluid that's up here. It's moving through some water in a beaker, and say it's a marble, right? This marble's moving downward through this water, but the water is exerting a drag force, and the drag force is pushing it back up. Now, marble's pretty heavy, pretty smooth. If it has enough mass to it, it'll exert enough force that it'll sink pretty fast, right? If you've dropped a marble in water, water doesn't exert that much force. But if you drop something lighter that has more surface area, then it might take a longer time to float down through the water. But right for this one, the drag force is exerted in the opposite direction. The opposite direction. In the opposite direction. And I'll abbreviate that so we can move on, of the object. The drag force is dependent on the properties of the object. Yeah, we talked about the marble, and we talked about something that had a little less mass but more surface area perhaps. The properties of the fluid, obviously, if you have a thicker fluid like oil or dishwashing liquid, it might exert more of a drag. And the motion of the object. Yeah, is the object going down? Is it flowing sideways? Yeah, so this is obviously a true statement. I'm going to move on to the other guys. A light object with a large surface area is less affected by drag force than a more compact object is when both objects are falling. And we already know that I just answered this question, right? It's actually not less, it's more affected, right? Because if you think about it, if you drop a feather that has less mass but more surface area on top of the water, will it sink? Well, it might eventually become a little bit waterlogged and start to sink, but that marble falls through the water right away and falls pretty quickly. But that feather, even if it gets waterlogged, will fall very, very slowly. The terminal velocity of a falling object is reached when the object impacts the surface. No. We know that terminal velocity occurs when the drag force is equal to the force of gravity. Sorry it took me so long to write that. Holy cow. Didn't realize it was going to take me a year and a half. So there we are. We have those problems all set for us. We'll move on because this is going to be a pretty long video. This is simple true and false stuff. This is really good. This just talks to us about tension. And when we want to know about tension, tension is the force exerted by a rope, or a string, or a chain, or a cable. All right, so think of those things: ropes, strings, cables. Those things, like they all exert tension. So a book sitting on a table, does that involve tension? Not on your life. A chandelier hanging from a ceiling, yeah, that cable there involves some tension. Two teams playing tug of war, you bet. That rope in the middle, that has tension. And an automobile moving along a road involves tension. Now, there might be some sort of chain or something in there, not usually with a car, so we're definitely going to say false. An elevator moving in a building, yeah, there's a lot of tension in there, right? Because there are cables that move the elevator up and down. A basketball pass from one player to another, no, there's no string in there unless you play for the Harlem Globetrotters. A horse pulling a cart, yeah, there could be some tension there. There could be some sort of harness there that is like a rope. It could be some sort of leather or something like that. Oftentimes it is some sort of wooden harness or metal harness as well, but there is some sort of leather part that gives it some malleability. Okay, a truck towing a boat, yeah, I would say that has tension. Again, there's metal there, but you know, it's tough to say, but I'm going to say yes, there is some sort of chain involved. Water skiing definitely involves tension. A trapeze definitely involves tension. Paddling a canoe, not on your life. Surface tension, maybe, but that's not the tension we're talking about. And then parachuting, of course, there are ropes involved with parachute. All right, so that was pretty easy. Go back over that if I went too fast. Now we're going to draw some free body force diagrams to show the forces at work when you first step out of a plane, right? Just before the air resistance gets to you and you first step out of the plane, the only thing that affects you, of course, there's some wind resistance pushing you horizontally or what feels like horizontally, but really the only thing that's pulling down on you is the force of gravity, all right? Draw a free body force diagram when you are in free fall. Okay, and you haven't. Let's just say for our purposes here, you have not reached terminal velocity. I'm sorry, I made FG a little bit larger, but let's put the other vector in there, the other force vector in there, and we'll make it a little bit of air resistance, right? I would call this the force of friction or drag, right? There's drag. Air resistance is drag, or when we get to it, we could call it friction, air resistance being friction. Either way, you can call it drag or friction. Last but certainly not least, we have, again, you pop your parachute, and then you have the force of gravity. And once that parachute opens, you either are not accelerating or you are accelerating at a very, very, very slow rate. So what we're going to do is we're going to show this upward force vector to be just about the same as the force of gravity. All right, so we could call that tension, because we just called a parachute has tension, those lines on it, right? And that tension is pulling upward while gravity is pulling you downward. And that's really it. Pardon me. Now, for posterity's sake, now you have me coughing in a video. Sorry. All right, moving on. This is the problem-solving portion of the show. And this one isn't that difficult. This isn't the part that's difficult. This is just versions of F equals MA, F equals MA, F equals MA, but this is M equals F over A. Remember, Newton himself said that A is equal to force over mass, right? And we don't need to worry about that, so I'm going to get rid of it because it's not part of what we're doing here. Okay, so F equals MA. We're going to do some work. You ready? All right, the force required to accelerate a bowling ball at 2 meters a second squared forward, right? And all we're going to do is the force required to make that mass accelerate that much, let's multiply these two things. So we have 6 kilograms times 2 meters a second squared. So the force is going to be equal to 12 newtons, right? Kilogram meters a second squared are newtons. All right, and let's move on to the next one. So we have, what is the mass of a cat that weighs 30 newtons? Now I need to open up my calculator, so just give me one brief moment to open up my phone to get to where my calculator is. I'm going to talk to you while I do it because I finally got there. So I have it written out here for you. Sorry about the time it took for me to open that up. We have 30 newtons divided by gravity, which is 9.8 meters a second squared. I could have written F over G, right? Because I used mg down here. And then that is equal to, let's see, 30 divided by 9.8 is approximately just about, let's do this, which is just about 3.1 kilograms. Let's put it in 1 decimal place there. We could say it's just about, because we have significant figures here, right? So to the nearest tenth, I could say, or I have 3 significant digits, so I could say 3.06 kilograms. Cool. I will accept that one. I like rounding to the first decimal place. It's usually pretty good for me. How large is the tension in a rope supporting a 4.2 kilogram bucket? Again, we'll just multiply that 4.2 times the acceleration due to gravity, and let's see what happens. 4.2 times 9.8, and I should have about 41, just about, where are we? Just about 41 newtons of tension. Okay, and last but certainly not least, this is a super easy one. I may change the number on here just because it's so super simple. There is a net force pushing upward on this object of 125 newtons. So, hey, what is the single force that will produce equilibrium? Well, if there's 125 of net force upward, we need 125 newtons pushing downward. Right? And then this object will stay still. Sound good? That's nice and easy for you. See, we haven't done anything really difficult yet. Here's where the bigger numbers come in. It gets to be, it looks annoying. I'm going to use some estimation in here to make this work out really well. A rocket weighs 2 times 10 to the 7th newtons. Its engine exerts an upward force of 25 times 10 to the 6 newtons at liftoff. What is the mass of the rocket at liftoff? So we're going to go and find that mass. And to find that mass, all we have to do is divide 2.0 times 10 to the 7th by 9.8. Well, I divided by 10, because then you just knock this exponent here down one. You just divided by 10, knocked one of the zeros off, and this is your mass, right? Because we said that mass is equal to force divided by gravity, right? So there's our force, our weight, which is a force, divide out the gravity, and you have your mass in kilograms. Okay, well, I have all that information now. I'm going to do some more math. What is the acceleration when this rocket lifts off? All right, well, here we go. Acceleration is the force divided by the mass. Okay, well, let's find out. We've got those forces, right? We have the force, the object's weight, right? And we have the force at liftoff. And if I do a little bit of work here, I can see 25 times 10 to the 6th. This is actually, if I move the decimal point over 1 and drop this exponent, now I have 20 times 10 to the 6th. So 25 times 10 to the 6th minus 20 times 10 to the 6th is easier to see, right? So 25 minus 20 is 5 times 10 to the 6th newtons divided by the mass of the object. Oh, look at this. 2 times 10 to the 6th kg. Right? So newtons cancels out. What we're left with is, with kilograms, what we're left with is meters a second squared. 10 to the 6th cancels out with 10 to the 6th. And 5 divided by 2 just gives me 2.5 meters a second squared. See how easy that one was? Don't forget, you have the object's weight, right? You have the force of thrust. That's this guy here. So the thrust is pushing upward. What's pulling back down on it? The force of gravity, right? So force of gravity. Force of thrust. Let me get rid of that. Give myself some room. The force of the thrust. Right? And so there's a little bit left over, and that little bit left over is that 5 newtons, or 5 times 10 to the 6 newtons, and we have an acceleration of 2.5 meters a second squared. Sorry it took so long for that. This is the last problem. I like this problem. I think it's a great problem to have on here. I'm going to change these numbers, all of these numbers when we get to the test. But I don't want you to fail a test. I like the true-false questions. I may leave those alone. Definitely going to leave the definitions alone. Probably won't mess around with the italicized words or anything like that. So these things, just messing around with numbers isn't going to be such a big deal. So we have a stepping stool is constructed so that it collapses when the normal force exceeds 1,100 newtons. So if you are heavier than 1,100 newtons, your weight is greater than 1,100 newtons, the stepping stool will collapse, right? Anything over 1,101, it collapses. And he falls 6 feet to his death. I don't know. He won't fall that far, but it's just a step stool. But he doesn't want to collapse because he's reaching up to weld, okay? You're assisting a welder who weighs 106 kilograms. I put that down here, right? Here's his weight, Okay, and I'm going to go ahead and calculate this and put it down here. And then you pass him a torch and a fuel tank that have a combined mass of 14 kilograms times 9.8 meters a second squared. That is the weight of the tank. And when we combine these two things, when we add these two things together, if that combined weight is greater than 1,100 newtons, you're going to be able to tell me whether this is okay or not. The welder refuses to take both items from you, and you're going to tell me why. And all you're going to do is show me your calculations for weight. So we have 106 kilograms, 106 kilograms times 9.8 meters a second squared. And this right here has a weight of 1,038.8 newtons. Okay, so far we're getting pretty darn close. We only have, what is that, 61.2 newtons left before this thing is right at its max level. And if you look right here, we know we have more than 61. Right, but let's go ahead and do the calculation. 14 times 9.8 gives me 137.2. And if we add those two things together, 1038.8, we get a grand total of, oh, sorry, I didn't mark it as newtons. We add them together, we get 1,176 newtons. He doesn't accept it because he knows that he's too close to the weight limit. Okay? When you're a guy like me who is 100 kilograms, you know when things are getting close to that weight limit. So I wouldn't be able to accept that thing either. 980, I'd be over the top by, about, 16, 17 newtons. So, see what I mean? Okay. That's it, guys. That's the whole video for you. If you have any questions, please let me know. I thank you for your time, and I'm sorry this is such a long video. Take care.